Hi, this is Qiao Chu at Lehigh University. Today we're going to talk about the problems in homework 1 for CEE222, Water Resources Engineering. Let's take a look at the first problem, which is using mercury banometer to measure the pressure in the pipe. So here is an open-ended mercury banometer. We already know that H1 is 3 feet and H2 is 2 feet. To solving this problem, first we need to identify an equal pressure surface, which is at the intersurface of mercury and water. So the point on the surface should have the same pressure, which means that the pressure on point 1 and the pressure on point 2 should be the same. Then P1 is equal to P2. So the pressure on the point 1 is exerted by the column of mercury on the top of the point. Then P1 is equal to the specific weight of mercury times H1. The specific weight of mercury can be represented by the specific gravity of mercury times specific weight of water. Then do not forget times H1. The pressure on point 2 equals to the P plus the pressure exerted by the column of water. So the pressure would be the specific weight of water times H2 plus P. This is our third equation. Then we can bring equation 2 and 3. Into equation 1. We can get an equation like the specific weight of mercury. It's specific weight of water times specific gravity of mercury times H1 is equal to the specific weight of water times H2 plus P. Because P is our unknown, we want to put it on the left-hand side. It would be the specific gravity of mercury times H1 minus H2 times the specific weight of water. Then we can bring the value that we already know to the right-hand side. The specific gravity of mercury is 13.6 times 3 feet and minus 2 feet. Then we need to times the specific weight of water, which is 62.4 pounds per cubic foot. Then we can get a value which is 2,421 pounds per square feet. And then we want to represent that in psi, which is equals to 16.8. And because the problem also asks us to represent P in the height of Mercury, so the height of Mercury would be P over specific weight of Mercury. Which is equal to the P over specific gravity of Mercury times specific weight of water. Then we bring the value into this equation. It would be 2,421 pounds per square feet over 13.6 times 62.4 pounds per cubic feet. And after the unit transformation, we can get a final result, which is 34.24 inch of mercury. Okay, let's take a look at the second question. A circular gate is installed on a vertical wall as shown here. Determine the horizontal force P necessary to hold the gate closed. Neglect friction at the pivot. So to solve this problem, we want to put a coordinate on top of the figure first. We determine the x-axis is the intersection line between the free surface and the wall. So the x-axis should insert it into the board. And then the y-axis is along the wall and perpendicular to the x-axis. So here is our y-axis. And the angle between the free surface and the wall, we call it theta. In this problem, theta is equal to 90 degrees. To determine the horizontal force, we need to figure out the magnitude of the hydrostatic pressure, F, and its location. We call the location here is YP. Okay, to determine the magnitude of hydrostatic force, we use the equation F is equal to specific weight of water times sine theta times the area of the circular gate times y bar. The y bar here is the coordinate of the centroid. Because the sine theta equals to sine 90 degree equals to 1. And the area of the circular gate is 1/4 times pi the d squared. and the y bar here is equals to h. So if we bring this three sentence into this equation, we will get the magnitude of force is equals to specific weight of water times h times pi times 1/4 times d squared. So the second step is to determine the location of the force, which is yp. We use the equation according to the equation given on the textbook. So the number of equation is 2.16 on page 24. It shows that y sub p is equal to the moment of inertia of a circle over a times y bar plus y bar. And according to table 2.1 on page 25, we know that the moment of inertia equals to 1/64 times pi times d to the power of 4. And area is 1/4 times 1 pi times d squared, and y bar is equal to h. So bring this three equation into this into yd. So we can get yp here is equals to d squared over 16 times h plus h. Because the question told us that the gate is get closed, so the moment at the pivot should be 0, which means that sigma m equals to 0. The hydrostatic force times its distance to the pivot is, it should be yp minus h. Minus the horizontal force p times distance, which is half of the diameter, is equal to 0. So after rearranging this equation, we can get P is equal to 2 times F times yp minus h over d. Because we already know the F and the yp, so we can bring those two equations into this one. Then we can get P is equal to specific weight of water times pi times d squared over 32. So it should be noted that when we calculate the magnitude of F, we use the y bar, the distance to the coordinate of the centroid, but it's not, y bar is not the location of the force. So the location of the force is yp. So we need to differentiate these two terms. Okay, let's take a look at the problem number 3. There is a horizontal commercial steel pipe. Its 1.5 diameter carries 3.5 cubic meter per second of water at temperature 20 degrees Celsius. We need to calculate the pressure drop in the pipe per kilometer length. Assume that the minor losses are negligible. So we already know the flow rate and also the diameter. The first step, we can calculate the velocity. The velocity is equal to Q over A. A is the area of the pipeline. Is 1/4 times pi times d squared. And then we can bring the value into that equation. The velocity is 1.98 meter per second. After we know the velocity, we can pick 2 points to write down the energy equation. We choose a point 1 at the upstream and point 2 as at the downstream. So at the point 1, H1 plus P1 over specific weight of water plus V1 squared over 2G is equal to P2 plus P2 over specific weight of water times V2 squared over 2G plus the head loss. Because it's a horizontal pipeline, we know that the H1 should equal to H2. And the diameter of the pipeline is constant along the line, so the velocity at these 2 points should also be the same. And it told that the minor loss is negligible. So the head loss is equal to the friction loss. Then we can bring these 3 equations into the energy equation. Then we will know that the pressure drop equals to P1 minus P2 is equals to the specific weight of water times friction loss. Because we know the temperature is 20 degrees Celsius, we can know the specific weight of water. Then the next step is to calculate the friction loss. The friction loss is given by the Darcy-Weisbach equation, which is HF is equals to friction factor times the length of the pipe over diameter times velocity squared over 2g. The friction factor is determined by the relative roughness and also the Reynolds number. We know that it is commercial steel. So if we search the value on table 3.1 on page 66, we can get the roughness is equals to 0.045 is millimeter. Then we can calculate the relative roughness is equals to 0.045 over the diameter is 1,500 millimeter. So we can get a relative roughness here. We know the water temperature is 20 degrees Celsius. So the table 1.3 on page 6 give us the kinematic viscosity is equals to 10 to the power of minus 6 square meter per second. Then we can calculate the Reynolds number is equals to diameter times velocity over viscosity. Diameter is 1.5 meter. The velocity is 1.98 over viscosity is 10 to the power of minus 6. We get the Reynolds number 2.97 times 10 to the power of 6. So based on the relative roughness and also the Reynolds number, we can search the friction factor on Moody diagram. Which is figure 3.8 on page 68. We can get a value. Friction factor is equals to 0.011. After we know the friction factor, we can calculate the value of the friction loss. So friction loss is equals to 0.011 times L is equals to 1,000 meter. Diameter is 1.5 times the velocity is 1.98 squared times 2 times 9.8. So the friction head loss is equal to 1.47 meter. And as we just mentioned, at temperature 20 degrees Celsius, if we search the specific weight of water on table 1.2 at page 4, the specific weight of water is equal to 9,790 Newton per cubic meter. Then we can bring these two values into this equation. The pressure drop is equals to specific weight of water times the friction head is equals to 9,790 times 1.47. It equals to 14.4 kilonewton per square meter. Let's look at the problem 4. It asks us to determine the flow rate of water with a temperature of 20 degrees Celsius that will cause a pressure drop of 70,250 Newton per square meter in 350 meter of horizontal cast iron pipe with a diameter of 60 centimeter. Ignore the minor losses. So the first step to solve this problem, we want to write energy equation. For the point 1 and point 2, it would be H1 plus P1 over specific weight of water plus V1 squared over 2G equals to H2 plus P2 over gamma plus V2 squared over 2G plus the head loss. And because there is a horizontal pipeline, then H1 is equals to H2. And because the diameter is constant, then the V1 is equals to V2. And it also said we should ignore the minor loss. Then the head loss is equal to the friction loss. If we bring these three equations into the energy equation, then we can get the friction loss is equals to pressure drop over specific weight of water. We know the value of delta P, so we can bring the value into that equation. The specific weight of water at a temperature 20 degrees Celsius, it's 9,790 Newton per cubic meter. So the value of friction loss is 1.76 meter. And friction loss can also represented by the Darcy-Weisbach equation. The friction head is equals to the friction factor times L over D times V squared over 2G. The friction factor is determined by the relative roughness and the Reynolds number. And because it is a cast iron pipe, then we can find the value of the roughness in the textbook is equals to 0.26 millimeter. Then we can calculate the relative roughness is equals to 0.26 over 600 millimeter. It equals to 0.000433. And because the water temperature is 20 degrees Celsius, we can find this kinematic viscosity is equals to 10 to the power of minus 6 meter square per second. Then the Reynolds number would be the velocity times diameter over the kinematic viscosity. Currently, we do not know the value of velocity, so we use v to put here as an unknown, and the diameter is 0.6. The kinematic viscosity is 10 to the power of minus 6. So currently we have three parameters: the friction factor, the relative roughness, and also the Reynolds number. In this three parameter, we only know the number of the value of the relative roughness, so we cannot use a Moody diagram. But we can make an assumption of the friction factor. Then we can calculate. We have two known numbers. Then we can use a Moody diagram to validate our assumption. So we assume the friction factor it's equals to 0.017, and the fluid is complete turbulence in a rough pipe. So based on the friction factor, we can calculate the velocity here. So HF is equals to 0.017 times L is 350 meter over 0.6 times B squared over 2 times 9.81. Because we already know the value of the friction factor in the first step, so it's equals to 1.76 meter. Then we can calculate the velocity is equals to 1.87 meter per second. And we can bring this value back into the Reynolds number equation. Then we can get the value of the Reynolds number. It's equals to 1.12 times 10 to the power of 6. Because we know the friction factor and the relative roughness, then we want to use a Moody diagram to validate, to find the Reynolds number, to compare the Reynolds number that we calculated to see whether or not it is a good assumption. So the next step is to check the values in the Moody diagram. We know the friction factor is, we assume it is 0.017, and also the relative roughness is equals to 0.00043. And after we search the Reynolds number on the multi-diagram, we find that the Reynolds number is close to 1.12. It's close to our assumption. So we find that the assumption that 0.017, our friction factor, is equal to 0.017 is okay. Then we can calculate the flow rate by using velocity times the area is equals to 1.87 meter per second times 1 Fos times pi times 0.6 squared. So finally we can get the flow rate is equals to 0.529 cubic meter per second. Let's see the problem 5. A water flow through a 4 centimeter wrought iron horizontal pipe, and the pipeline, the length of the pipe is 50 meters. It contains one fully open gate valve and 2 elbows. We already know the pressure at the downward, which is point B, is equals to 192 kilopascal, and the flow rate is 0.006 cubic meter per second. We want to know the pressure at the point A, because we already know the flow rate and also the diameter. So the first step is to calculate the velocity. The velocity is given by the equation V is equals to Q over A. A is equals to 1 Fos times pi times d squared. So we can bring the value into that equation, and the other result is 4.77 meter per second. The second step is to write down the energy equation for the point A and point B. So it would be HA plus PA over gamma plus VA squared over 2G equals to HB plus PB over gamma plus VB squared over 2G plus the head loss HL. And because it is a horizontal pipe, so the HA is equals to HB. And because the flow rate and also the diameter are constant, so VA is equals to VB. And because the pipeline has a gate valve and also two elbows, the head loss in this pipe is equals to the friction loss plus the bend loss and also the loss caused by the valve. So if we bring this three equation into this one, we can get the pressure at point A is equal to the pressure at point B plus HF plus HB plus HV times specific weight of water. Because the pressure at the point B and the specific water is given, so the next step is to figure out the value of each friction, each loss. So the first one would be, we want to figure out the value of HF. HF is given by the function friction factor times L over D times V squared over 2G. Because it is a rough iron, we can read the number of the roughness in textbook is equals to 0.045 millimeter. Then we can calculate the relative roughness is 0.055 over 40 millimeter equals to 0.00113. And because the temperature, we assume that is this 20 degrees Celsius, then the viscosity, kinematic viscosity, is equals to 10 to the power of minus 6 square meter per second. And the specific weight of water, it's 9,790 Newton per cubic meter. Then we can calculate the value of Reynolds number is equals to the diameter times velocity over the kinematic viscosity. It's equals to 1.91 times 10 to the power of 5. So based on the relative roughness and also the Reynolds number, we can find the friction factor on Moody diagram. Then the friction factor, it equals to 0.022. The next step is to calculate HB. HB is given by the equation the coefficient times V squared over 2G. Because we have two elbows here, so we need to times 2. Because the elbow with R over D equals to 4, we can search the value on page 80. We can get KB is equals to 0.17. Then we find the equation for the HV. HV is given by the equation the coefficient times V squared over 2G. And because it's a fully open gate valve, we can search the coefficient in a table 3.6 on page 80. We can get the value KB equals to, it should be KV. .15. Then we need to bring values or equations to PA, which is this equation. So we can rewrite this equation like pressure A is equals to pressure B plus F times L over D plus 2KB plus KV times V squared over 2G, and then times specific weight of water. Then we can bring the value back to this equation, which is PA is equals to the pressure at point B is 129 kilopascal plus the friction factor is 0.022 times the length is 50 meter over the diameter is 0.04 and plus 2 times 0.17 plus 0.15, then times the velocity is 4.77 square over 2 times 9.81, then times the specific weight of water, which is 9,790. Then we can get the value of the pressure at point A is equals to 110 kilopascal. Now let's take a look at problem 6. There is a water tower which is 34 meters high, supplying the drinking water to the original area. The pipeline is a commercial steel and it's a horizontal pipe. The diameter of the pipe is 20 centimeter and the length is 800 meter. To increase the pressure head at the delivery point, the engineer proposed a new strategy, which is to increase 94% of the pipe into a large size, which is 30 centimeter, and then add 30-degree confuser to connect the remaining part of the pipe. We already know the water temperature is 20 degrees Celsius. The flow rate is 0.1 cubic meter per second. We want to know how much pressure head that gained by applying the new strategy. So to solve this problem, we need to calculate the difference of the head loss in these two strategies. So the first step is to calculate the head loss in the original one. So for the original strategy, the head loss is mainly contributed by the friction loss. So HL is equals to HF. And because according to the Darcy-Weisbach equation, HF is equals to friction factor times L over D times V squared over 2G. We know the flow rate and the diameter for the original pipe, so the velocity equals to Q over A, which is equals to 3.18 meter per second. Then next step is to calculate the friction factor, which is related to the relative roughness and Reynolds number. Because it's a commercial steel, so we can search the roughness in a textbook. The roughness equals to 0.045 millimeter. Then we can get the relative roughness is equals to 0.045 over 20 centimeter, which is 200 millimeter. Is equals to 0.000225. The water temperature is 20 degrees Celsius, so the kinematic viscosity can be searched on the textbook. It is equals to 10 to the power of minus 6 square meter per second. And then we can calculate a Reynolds number is equals to velocity times the diameter divided by the kinematic viscosity. It is equals to 3.18 square. Sorry, there's no square here. Times diameter is 20 centimeter and it is 0.2 meter over 10 to the power of minus 6. So it is equals to 6.36 times 10 to the minus 4, to the power of 5. So based on the relative roughness and the Reynolds number, according to Moody diagram, we can know that the friction factor is equals to 0.0155. Then we can calculate the friction loss for the original pipe. It is equals to 0.0155 times L is 800 meter long and diameter is 0.2 meter and times the velocity is 3.18 meter per second over 2 times 9.81. So the value of each of 0 is equals to 31.9 meter. And we can compare this HF1 to the height of the tower. It seems that the friction head used up almost all of the head. So the next step is to calculate the head loss and by applying the new strategy. The head loss in new strategy can be divided by the 3 parts. The first one is the friction head in the first part of the pipe, and the second one is the loss contributed by the confuser, and then the last one is the friction loss caused by this the remaining part of the pipe. So HF head loss here is new is equals to friction loss in the first part and loss contributed by the confuser, and then the loss in the second part. So the HF1 is equals to the Darcy-Weisbach equation, which is HF1 is equals to F1 times L over D times V1 square over 2G. We can calculate V1 equals to Q over A1. So the value is 1.41 meter per second. The next step is to calculate the friction factor 1 here. And because we already know the pipeline is made by the commercial steel, so the roughness is 0.45. Then we can directly to calculate the relative roughness in the first part of the pipe. It's E over D1. It is equals to 0.045 over 300 millimeter equals to 0.00015. And the kinematic viscosity is the same, keep the same, which is 10 to the power of -4. So the Reynolds number is velocity times d1 over kinematic viscosity. It is equals to 1.41 times 0.3 meter over 10 to the power of -6. It is equals to 4.23 times 10 to the power of 5. So based on these two info, we can determine the friction factor 1 by using Moody diagram. F1 is equals to 0.0155. And then we can calculate the friction head loss in the first part of this pipe is equals to 0.0155 times L is 94% of the original pipe, which is 0.94 times 800 meter. The diameter is 0.3 meter. Velocity is 1.41 square over 2g, 2 times 9.81. So we can get the value of the H1 is equals to 3.94 meter. Then we can get we already know HF1 here. So the next step is to calculate HC. HC is equals to the coefficient times V2 square over 2G. To determine the HC, we need to know the ratio of A2 and A1. A2 over A1 is equals to D2 over D1 to the power of 2. D2 is 0.2 meter and D1 is 0.3 meter. So its ratio is 0.444. That after we get the area ratio, we can search the coefficient in figure 3.11 on page 77. And we can get the K sub C is equals to 0.025. The velocity V2 is equals to the velocity in the original pipe because the flow rate and also the diameter keeps the same. So HC is equals to 0.025 times the velocity is 3.18 over 2 times 9.81. It is equals to 0.0129 meter. So the final step is to calculate the HF2. So comparing the second part of the pipe into with the original one, the only difference is the length. So the HF2 should equals to 1 minus 0.94 times HF0, which is 0.06 times 31.9. HF2 is equals to 1.91 meter. So after we know the value of this 3 parameter, we can get the value of the head loss in a new strategy. It's 3.94 plus 0.0129 plus 1.91, which is equals to 5.86 meter. So the head loss by applying this two strategy, it is equals to the original one minus the new one. It is equals to 31.9 minus 5.86. The delta H, the head loss, it is equals to 26.04 meter. So this is the result for this question. Take a look at the problem 7. There is a 16-feet cylindrical water tank, contains 10 feet of water, and there is a horizontal pipe with a rotary valve to drain the water from the bottom. The diameter of the pipe is 8 inch. So in this problem, we want to figure out how long does it take to drain 50% of the water in the tank. So the volume of water at time t is equals to the area of the water tank times the height of the water at time t. Because the area is a constant, so in other words, in this problem, we want to figure out the relationship between the water height and the time. So first of all, we want to pick 2 points. The point 1 is at the surface of the water. Its velocity is in this direction. And the point 2 is at outlet of the pipe. So for these 2, we can write down the energy equation for these 2 points. Sorry, it's H1 plus P1 over gamma times plus V1 squared over 2G equals to H2 plus P2 over gamma plus V2 squared over 2G plus the head loss. And because we said the datum is at the bottom of the water tank, so the H1 is equal to H, and point 1 is at the water surface, point 2 is at the outlet, so P1 is equal to P2 equals to the atmospheric pressure. Because the diameter of the water tank is much larger than the diameter of the pipe, so we assume that the changes of the water height is quite small. So, which means that we assume V1 is close to 0. And because the datum is at the bottom, so H2 is 0. And then the head loss, because the friction loss is negligible, so the head loss is equal to the loss caused by the valve, and also the square-edged entrance. And these 2 terms can be represented by their coefficient times V2 squared over 2G. So after that, we can get the equation H is equals to 1 plus KV plus KE times V2 squared over 2G. And in this equation, V2 is an unknown, so we want to put them on the left-hand side. Then V2 is equals to 2GH over 1 plus KV plus KE to the power of 0.5. Because there is a rotary valve, so we can search the coefficient kV on table 3.6. The coefficient kV is equals to 10. And because it's a square-edged entrance, so from figure 3.12, we can figure out K sub E is equals to 0.5. So the next step is to bring the values into the equation. It will be 2 times 32.2 feet per square second times h over 1 plus 10 plus 0.5 to the power of 0.5. Then we can get the velocity at point 2 is equals to 2.37 times h to the power of 0.5. Okay, let's see for the tank flow. Its flow rate Q1 is equal to the derivative of its volume to the respect of dt. Because the volume is equals to the area times h, and the area is a constant, so it can be represented by A times dH over dt. And A is equals to 1/4 times pi times d squared, so it can be represented by the pi times square d over 4 times dH over dt. It is Q1. So for the pipe flow, the flow rate at point 2, it equals to the area at point 2, the area of the pipe times the velocity at the point 2. It is equals to 1/4 time pi time d squared. Because we already know the V2, it is equals to this value, so we can bring it here, times 2.37 times h to the power of 0.5. And because the flow in should equals to flow out, so which means that Q1 is equals to Q2. So pi times d squared over 4 times dH over dt is equals to pi d squared over 4 times 2.37 times h to the power of 0.5. And these terms can be cancelled. So after we arrange this equation, dt is equal to the capital D over d squared times dH over 2.37 times h to the power of 0.5. Then we need to integrating. We can get t is equals to 1 over 2.37 times d over small d to the power of 2 times, because it's half of the 50% of the water, so the height is from 5 to 10. H to the power of minus 0.5 dH. So we can get a result is 1 over 2.37 times the capital D is 16 foot over the 8-inch is 0.667 feet to the power of 2 times 2 times 10 to the power of 0.5 minus 5 to the power of 5. Then we can get the result. So it takes 450 seconds to drain half of the water in the cylindrical tank.